Test, test. I'm going to do the introduction. This is Sean. He is annoyingly smart. Recently, it's true. I'm sorry. It's annoying. Recently, he applied for a PhD program and made the poor choices of choosing me as one of the people who was supposed to write up a letter of recommendation. And he still got in. I don't know how. But that's how life works. All right, he's going to talk to you. It's going to be amazing.
Thanks, Dave, I think. Is this working?
Yep.
All right, awesome. So another title for this talk probably would have been statistical crash triage, which is kind of what we're going to be talking about. So the motivation for this talk is pretty simple. Everybody thinks that the outcome of fuzzing when you find bugs is happiness. It's not, it's actually misery. Because you're condemning yourself and your co-workers to a lifetime of sitting in a debugger trying to figure out what the hell went wrong and why all the software sucks. And ideally what we want to do is augment that process a little, so by the time you get to the debugger, and your life is still going to suck, that it sucks slightly less. So most people's tooling for fuzzing looks a little bit like this. You have some source inputs, you throw them with your fuzzers, you get out a bunch of crashers. With those crashers, you perform minimization, bucketing, that kind of thing, so you end up with, like, say, per bug sets of inputs. And then you take those per bug inputs and you feed them whatever unfortunate has to deal with them. And then they use like GDB or Query, whatever, and a certain amount of automation in order to figure out exactly what the root cause is. There's a bunch of different places you can jump in this workflow and actually kind of automate different things. So where this talk is going to jump in is in this process here. So right after we have crashing inputs and we have a bunch of source inputs, if we can perform some analysis over those, provide a per bug triage report, and then feed those plus the crashers to a human who will then continue with their miserable existence. So what is a useful triage report? And this is obviously subjective, right? Somebody who's an experienced developer with a piece of software will desire different things from a triage report than somebody who's kind of coming to it for the first time, or even if they're just if they've had a little experience with it. Also, if you want to patch a program, you probably want a different type of triage report than if you're trying to exploit it. So you need to kind of come down somewhere on the type of information that you actually want to provide in such a report. And where we're going to come down on this is what I want, conveniently, because I was the one doing the talk. So to give you an idea of the type of kind of end result we're going to be working towards, we're going to quickly kind of work through a fairly simple example. This example is from PHP. PHP is a great tool if you do like kind of vulnerability research where you're happy to kill the bugs because it's riddled with bugs and it represents pretty much every bug class in existence in an open and accessible format. So this particular bug is an out-of-bound read in the XML parser set option function. And there's kind of two important things in the kind of the executive summary of it. The first is the function allows one to specify a number of bytes to skip beyond the start of the tag, and the other part is the value is not sanitized in any way. So what we're kind of aiming for here is that we want to provide, should I move this closer to my mouth? Seems like it's pretty good. So we're going to provide to the analyst is enough information that allows them to kind of draw both of these conclusions. They can figure out where the bytes are being specified, they can figure out it's not sanitized, and they can kind of figure out what the outcome of that is. So the proof of concept for this bug, or like the test case discovered by a fuzzer in this case, has two parts that are important. The first is actually this part down here at the bottom, which is the XML parser set option function is being told to skip, if we assume this is a side integer, and it's being told to skip like 4 bytes before the start of the function. And then later, when actually parsing a tag, this start element function will be called, and that buffer will be echoed. So effectively what's going to happen is, every time we get to a tag, we're going to jump 4 bytes before it, we're going to create a string object from that, and then that's just going to be printed. So it's like a stupid little information leak. It doesn't really, it's not particularly important, but it kind of serves the purpose for this example. So the root cause of this is fairly straightforward. There's two parts. There's the XML parser set option function, which simply takes in a PHP Z value, converts it to a long, and then stores that in the t-offset attribute of the parser. And again, we can see there's no sanitization being performed here. The assumption is that the user of this value will sanitize it. And then in the start element handler function, so much later in the execution, that t-offset value is taken, it's added to a character pointer, and a string value is created. So again, if that's -4, it'll jump before the start of that tag, it'll create a string value from it, so your string will be 4 bytes and then the actual string, and then that goes on to be printed. So if we want to describe the root cause of this bug, we can effectively construct a predicate that looks something like this, like a safety invariant, which is if this holds, then this bug doesn't exist. If the t-offset value is always greater than or equal to 0, or if it's always less than or equal to the length of the string, then everything's safe. If that holds here, then it's perfectly fine. On all buggy runs, this holds. So either the t-offset is less than 0, or the t-offset is greater than the length of the string. So the question is, say for example, if we could discover this and report it, is it sufficient to understand the bug? If we could just produce this. And realistically, it isn't, because it doesn't give you any contextual information. It doesn't tell you where those values come from, and it doesn't tell you where they go. So a better result in this case would be that in the x1 parser set option function, if we could, for example, say that on a lot of buggy runs, the t-offset is less than 0. And then we can give the same predicate in the start handler function, which is the actual root cause of the bug. What this does is it gives us the actual root cause of the bug, and it gives us some other things that describe, or they give contextual information that allows a user to basically tell where the variables in this actually came from. So the second predicate is an invariant. It perfectly correlates with the program actually crashing. In 100% of the bugs, or 100% of the crashes, this thing is true. Whereas the first predicate it's a detectable anomaly. It doesn't always hold, but it correlates sufficiently strongly with the crash that it probably has something to do with it, right? So it could be the case that in some of our crashes it's because the t-offset is greater than the length of the string, but we'll say if in a lot of them this actually holds, then that's something worth reporting. The point here being that we want to report things that both correlate with a crash and that cause a crash. Things that cause a crash are kind of like that root cause. They can be quite specific if you want to be able to create a perfectly descriptive formula. And things that correlate with a crash help explain that root cause. So the reason correlation is important, as well as actually explaining root causes, a lot of the times the predicates that describe a root cause are incredibly precise and very difficult to discover. So in situations where we can't actually discover the precise root cause, if we can discover things that still correlate quite strongly with the crash, they would be worth reporting, and they can help guide a user to actually discover what the true root cause is. So takeaway point here is that it's not sufficient to just have the whatever predicate perfectly describes the crash. You also need kind of other things that correlate strongly with the crash. All right. So it's really embarrassing if I couldn't open this. Okay. So when I was saying we needed to kind of come down somewhere on what our actual output of this thing is, the output form is going to be an invariant which is true in all buggy runs and false in all non-buggy runs, and as many explanatory invariants as possible, or anomalies, which enable the user to construct a series of events from the input being read into the system to the bug being triggered. So, the remainder of this talk is very straightforward. We're going to briefly talk about some prior work in this area because there is quite a lot of academic work. We're going to talk about something called crash corpus, which is an evaluation corpus for this work. The crash cycle is the actual tool itself, and then a conclusion. The code for this is available, in that it's available if you send me an email and I'll add you to the GitHub project. It'll probably be publicly available in like 6 months or so. But if you're here, just send me an email, tell me you're on Infiltrate, I'll add you to the project, and you can use everything. All right, so the prior work for this is extensive and useful in some ways and incredibly not useful in others. In the academic literature, they typically report results of the form, this line or this function correlates with a crash. And the issue with this is that it assumes that if you tell a user that a line correlates with a crash, they can determine, based purely on looking at that line, no contextual information, whether it does or does not. It's this thing called perfect bug recognition, basically, which is that if you give a user a list of lines in a program with a score saying which ones correlate more strongly with a crash, that if they scan from the top of that list down to the bottom of that list, they'll be able to pick out exactly the lines which actually are responsible for the bug, even if they have no contextual information. That's kind of a nonsense assumption, because very few people can do that for bugs that are anyway complex, because, I mean, lines of code can be buggy or non-buggy depending on, say, the values of the processing of those kind of things, right? So that's one issue with the kind of the academic prior work. The other issue is they tend to assume that there's like one bug per program and like one bug hit by all inputs, which makes kind of some of the math a bit easier. And again, that's a little bit kind of unsafe. So what we kind of end up with from the prior work is we have a huge, like 16 years of literature that has a number of really interesting algorithms in it, but it's quite hard to tell which ones are actually applicable because the evaluations are questionable. And it's also quite hard to tell which ones are applicable because not only are the evaluations questionable in terms of how the results are presented, but they tend to be on quite small targets. So the first kind of step for this work and how we're going to talk about this crash corpus thing is effectively that I had to construct my own corpus to begin with in order to evaluate my work, otherwise I wouldn't really know where I was going. Effectively what I ended up doing is taking the academic literature, taking the algorithms that kind of I had a gut feeling might work and had the lowest implementation cost, and then working from there, evaluating them on this crash corpus thing, and then just iterating. So the goals of the corpus are pretty straightforward. We want a diverse set of targets and bug categories. We want to replicate the starting point from crash triage in real situations. So effectively you want your crashing inputs, your non-crashing inputs, no other processing, and then just they're there. You ideally also want like push button build and execute of all targets. Like one of the huge issues with academic corpuses is like, all right, so I want to compile PHP, I figure out all the dependencies, and I compile that. Then, okay, I want to like compile something else, I got to figure out the dependencies, and then so on and so forth, and eventually you just go insane and give up. So I've got around that problem basically by creating a Docker instance for every target in the corpus. And also, the other issue with evaluation for these things is trying to figure out like the different environment configurations and input flags and that kind of thing. So there's like a /run script for every target. You provide a single input, it executes that target on that input, like boots up a Docker image, runs it on the input, and then dumps out your analysis results to disk. So ideally, you never have to worry about build or execution details. All the bugs are pre-triaged. In other words, for every bug, you get like a little JSON file describing exactly the lines in the program where things go wrong, so you can actually evaluate, like if you predicted that line was relevant or not, you know whether it is, and it's pretty easy to extend. So the current state, as you can see, we haven't quite, this is a pain in the ass to build because everything needs to be triaged. So there's only a single target at the moment, which is PHP, which is a significant weakness in the actual corpus, but I'm in the process of integrating like JavaScript parsers, so this is something that is nearly alleviated. There's about 8 bugs in total, but they're sufficiently representative of like interesting bug classes that I think the conclusions that I'll draw the rest of the talk are relatively solid. There's everything, there's use after freeze, out of bounds reads, writes, null pointer to references, and that sort of thing. The other thing that you kind of want in the corpus is that it actually is representative of programs that are relatively along, or at least along the size of things you want to analyze. And PHP, despite being complete shit, is actually pretty complicated. So there are still some weaknesses in the corpus, but everything, all the other objectives other than a diverse set of targets is basically achieved so far. All right, so crash site itself, like I mentioned, the plan was to effectively take the academic literature, get things that felt like they should work, validate those algorithms using a crash corpus, and then repeat until done. Or what actually happens is Infiltrate rolls around and run out of time. So if we recall our ideal result, we want an invariant which is true in all buggy runs and false in all non-buggy runs. And then we want as many explanatory invariants or anomalies as necessary to enable a user to actually construct a series of events from input to actually that occurring. So just a quick aside, this is something that's going to be kind of core to everything else we're going to work on. Everybody here, I'm sure, knows what a predicate is, just so we're all on the same page. It's a Boolean valued function. The function takes one or more inputs and then gives you like either true or false as a result. Then we have this concept of predicate synthesis. It's a brute force approach to coming up with predicates based on templates. So you start off, you have templates. These are variables that are going to be replaced with like stand-in variables. So you could have a template such as x plus y is greater than 0, x plus y less than 0, x plus y is equal to 0. You then have variables that you actually observe at runtime. And then you slot those variables you observe at runtime into these functions to synthesize real predicates. And then based on values you then observe at runtime, you can associate true or false values with those predicates. So for example, if we observe the buff size is 16, I is equal to 18, we end up with these 3 predicates here and the evaluations on the right-hand side. So this is just something to keep in mind. This is effectively going to be the core of how we end up coming up with predicates. We'll brute force a huge amount of predicates, and then we'll just use a quick, not quick, statistical analysis in order to determine the ones that actually correlate with failure and those that don't. Okay, so handy explanation of what the algorithm is going to be. We determine the code relevant to the bug and instrument it together variable values. I'm going to explain how we'll do that in a second. If we can do that, we can then try and determine a useful set of predicate templates, synthesize predicates from those, and evaluate those predicates. We can then use the correlation between truth and falsehood of these predicates and crashing and non-crashing runs to determine which predicates actually correlate with the crash. And then finally, we can post-process those results into a narrative and present it to the user. All right, so there's a few assumptions in this. The first is that it's actually possible to predict the functions relevant to producing the ideal result. Right? If we can't do that, we're screwed because everything else depends on that. The second is that the number of functions that we can actually predict is sufficiently small that we can reasonably instrument them all quite heavily without impacting runtime to the point where just the analysis doesn't work in a real situation. The third is that given these values at runtime, we can actually synthesize a set of predicates that's somewhat useful and that we can actually form our ideal result from those. And the fourth is that if we have a list of ranked predicates, we can actually produce some sort of narrative that's in any way useful. So the remainder of the talk is going to be stepping through these predicates one by one and validating them. I say predicates, I mean hypotheses. So if these hold, the algorithm is this. Execute the target software on all crashing and non-crashing inputs, record the coverage information. From that, we can perform a statistical analysis of the coverage information to predict the relevant functions. Based on that, we can then instrument those functions to record every computed value. So this is why it's important that that set of functions is quite small, because if we want to record every single computed value, then it can't be a particularly large set, or we're not going to be able to do it a very large number of times, and we need to in order to get statistically sound results. We can then synthesize those predicates and determine the truth or falsehood, perform some statistical analysis of the truth or falsehood of those predicates to determine their correlation with the crash. And then finally, the last step would be to actually put those into, say, Vim or something like that, so you can actually have them at hand when you're automating code. All right. So determining the actual functions that are relevant to the ideal result. The approach is pretty straightforward. There's a huge amount of academic work on determining kind of line or function level correlation with crashing, with crashes. And as I said earlier, that's not particularly useful if you just give it to the user, because it's really hard for them to then go on to tell if your results are good or not. However, it does provide like a good first stage analysis to more in-depth, or good first stage results to more in-depth analysis. Doing this is pretty straightforward. We effectively take every target in crash corpus, compile it using the fsanitize coverage option from Clang, which will spit out line level coverage. If you're wondering why we're not using gcov here, it's purely because Clang and fsanitize coverage works perfectly fine with the dress sanitizer. So with gcov, if you have a program, you feed an input and that program crashes, you lose your coverage results. Whereas fsanitize coverage doesn't have that problem. It will always give you the actual coverage results, even if the program crashes, which is perfect for our situation. So that's fairly straightforward in terms of actually getting the coverage information. So then we actually want to rank those components. The academic literature provides this kind of family of functions for doing exactly this. It's called spectrum-based fault localization. I have literally no idea what they mean by that. The inputs are effectively a per component, and by component I mean like function or line, count of the number of crashing and non-crashing inputs. And the output is then a real valued score for that component, and the higher the score, the stronger the correlation between that component and the crash. The function, or the inputs are fairly simple. So we have EF, which is the number of crashing inputs on which the component is executed. And again, component here is a line or function or basic block, or whatever level of granularity you want to do your analysis at. EP, which is the number of non-crashing inputs on which the component is executed. NF, which is the number of crashing inputs on which the component is not executed. And then finally, NP, which is the number of non-crashing inputs on which the component is not executed. And again, these values are really easy to compute. We just execute the target, get the coverage results, and then count how many crashing and non-crashing inputs the component was executed on. So it's a very fast analysis. The actual functions themselves are also very small and very quick to compute, which means we can do them for a very large number of components across a very large number of inputs. So the Jacquard function, for example, is simply the number of crashing inputs in which a component is executed divided by the number of crashing inputs in which the component is executed, plus the number of crashing inputs in which the component is not executed, plus the number of crashing inputs on which the component is not executed. Again, you can see here it doesn't use NP, which is the number of non-crashing inputs in which the component is not executed. So some of the functions use some of the variables, some of them use other variables, and it kind of depends on what your kind of gut feeling or intuition is, like what contributes more to something being relevant for a crash. Is it the fact that it was executed on crashing inputs or that it wasn't executed on non-crashing inputs? So for example, this GP13 function, it only uses EP and EF, so it's saying NF and NP are completely irrelevant. And there's a whole bunch of them. In the in Crash Site, I implemented like 15 different ones because we hope that one of them can consistently predict the relevant functions regardless of the target software and bug class. If that isn't true, then it would mean that we would need to actually have some way of determining which function is useful for which target or bug class. Okay, so the evaluation for this, trying to determine the function which is most suitable for predicting crashing, components that are relevant to a crash is pretty straightforward. It's based on this concept of wasted effort, which is from the academic literature. It's quite simple. Basically, the wasted effort for a particular function is the number of components which are ranked higher than or equal to the number of functions that we consider relevant to the bug. So if the function ranks the relevant function as third in a list, then its wasted effort would be 3, because you need to consider 3 other functions before you get to the one that's actually relevant. If it ranked 10th, then the wasted effort would be 10. It's pretty straightforward. Okay, so in terms of selecting the best SFL ranking function, all I did was execute all of those analyses across every target and every bug, and we get results that look like this. So the 2 relevant columns, or the 2 ones we really care about, are this number of relevant functions here. That's the number of functions that are like truly relevant to the actual bug. That you would, like, there's a minimum set of functions you would need in order to actually understand why the program crashed. It's usually 2 or 1 for these particular bugs. This number of executed functions is the number of functions in the program that are actually executed. And then the minimum wasted effort is the final column. So what we can see is that for the vast majority of targets and bugs, the GP13 function can actually produce a pretty good ranking. For example, for this function here, the function that it predicts is most relevant to the crash is the first ranked function, which is exactly what we want. The worst case is this use after free in DOM processing, where out of 670 functions, the function which is actually relevant to the crash is ranked 32nd, which isn't ideal, but it's also not a complete failure, given that there's still a huge number ranked lower than it. So we effectively end up with the results that look like this. Basically, the hypothesis to me seems reasonable, that it's possible to predict the number of functions relevant to the ideal result. The minimum wasted effort was 1, the max is 32, and the average is 9. In other words, on average, if you take the top 10 functions, actually GP13 predicts are relevant to the crash, it will include within that the function that is in fact relevant. In other words, if you instrumented those top 10, you would be instrumenting the correct function as well as some of those. All right, so that's that one done. Hypotheses 2 and 3 are basically interrelated. 2 is that the number of functions relevant to producing the ideal result is sufficiently small that we can reasonably instrument them heavily. The thing is, in order to determine what we mean by reasonably instrument them heavily, we kind of need to know what the predicates, or sorry, what the values are that we want to gather. And the values that we want to gather will depend on the actual predicates we later want to synthesize. So hypothesis 3 is that given the values we gather at runtime, we can synthesize a set of predicates. So the question is, what do those predicates actually look like? We saw earlier the kind of idealized result for this particular bug was predicates that are kind of a relationship between a single variable and 0, or a single variable and a derived variable, so the length of a string or something like that. But that's just one example. So let's quickly consider another. There's this out-of-bounds heap right in PHP 5.7, or 5.5.7. The GD image crop function takes this crop structure. Pretty much everything in that crop structure is influenceable by an attacker. So it first of all starts out by passing crop width and crop height to this GD image create true color function. Inside in that, it allocates a bunch of buffers based on the crop width. It then performs a quick check, and if that check passes, it updates the crop width. And then finally, it performs a mem copy where it uses this new crop width, but it copies it into a destination buffer allocated using the old crop width. So it's quite straightforward code again. To understand the actual root cause of this, the analyst has a few questions they need to answer. The first is, how is the buffer size calculated? The second, how is the copy size calculated? And the third is, why does the copy size exceed the buffer size? So we need to think about what predicates actually correlate with failure and help answer these questions. So what predicates would we like to be able to provide the user with in order to allow them to look at that code and go, oh, well, this is the root cause, immediately without actually having to do a whole lot of analysis. And again, it's fairly straightforward. If we can tell the user that before line 57, crop x is greater than sx, well, at that point, we'll know that there's likely to be an integer underflow in the calculation of crop width. And again, if we tell them immediately afterwards the crop width is in fact less than 0, well, they know that for a fact. So if we can discover a correlation between these things and a crash, it will be quite useful. And that will tell us why the copy size exceeds the buffer size. And if we want to know how the copy size is calculated and how the buffer size is calculated, then we have something slightly more complex we need to tell them, because it involves two scopes. We need to tell them that the crop width times 4 is greater than sx, which is also crop width, by the size of int in a different function. So the conclusion we can draw from analyzing both this bug and all of the other bugs in the corpus is that we need to gather a few different things. We need all function return values, all variable values before they're used. We need all variable values after they're assigned. We need expression values, and then we need some custom handling for things like strings and callout and that sort of thing. You could gather a smaller subset of this and then kind of do like data flow analysis or whatever in order to propagate those values, but that sounds like work. So we can just instrument and then gather them. It's far, far quicker and it's far less effort. All right. So given that we know what we need to gather, in order to determine if we can actually reasonably instrument heavily, the only thing to do is actually go do that instrumentation and then see if it works out. For this, I used LTTNG, which if you don't use it and you do dynamic analysis, you probably should. It's like pretty quick, pretty reliable. It uses a common trace format. All it requires from you in order to actually do instrumentation and like data gathering is the trace provider specification, which is effectively the format of the records you're going to record. And it also just then requires you to modify your application in order to actually insert these trace points. And like if you take nothing, like literally nothing else away from this talk, like LTTNG being useful is a good one. The trace provider specifications themselves are pretty simple. For example, this is the format of variable values post-assignment. We record a file, a function, the line, the variable and its value. We actually record some other things as well, but it's basically that idea. And then for an expression, we record the file, the function, the line, the expression of the value. And then you just have this. So for return values, you have another one. For function arguments, you have another one. So you end up with like 5 or 6 different trace provider specifications. And then you just go and you rewrite your target in order to actually record those values. And this is incredibly simple. Again, you simply insert these trace points for everything you want to record, recompile your target, run it, and you get a quite nicely compressed trace of all of these values there. So in terms of actually performance impact, for less than 200,000 recorded events, there's no noticeable difference between this and normal coverage information. The reason being that Docker startup actually dominates both tracing and coverage information. So the Docker startup time is like a second or whatever, and the tracing excuse me, takes about the same. Above 200,000 events, you end up with like an extra second of runtime, say per 200,000 events. But realistically, if you're going above 200,000 events, and something else has probably gone wrong. Like if you're only instrumenting 10 functions, you shouldn't be getting more than 200,000 events. Like normally, you'll get something on the order of about 1,000. Things that can go wrong. The first is like Dave's pet peeve for any program analysis, which is, well, what are you going to do about loops, man? And the answer is like a pretty hacky solution where we're just going to log the first n iterations and like hope to God nothing relevant happens on the other ones. This actually works generally pretty well for this particular type of analysis, but not in all cases. And the second is kind of an artifact of what fuzz files tend to look like. You can have something, if you have a bug in an interpreter, your fuzz could have, or your fuzz file could have, say, 100,000 calls to a particular API with good arguments, and then one call to that API with the bad arguments. And if you instrumented on all of the bad cases, then you're going to end up with like a massive amount of completely irrelevant events. The solution to this is really just to minimize the test case, so you remove all of those extra things. Sometimes it's hard to do that, and in that case, you just use a timeout where, say, if it takes longer than 5 seconds to record everything, you just toss that test case away. And again, just hope to God nothing relevant happens after that 5 seconds. But this happens quite rarely. It's like there's maybe 1 or 2 tests in the whole corpus where that's actually a thing, and it doesn't impact the results in a particularly negative way, because you're talking about like hundreds of other inputs. So like statistically, it's irrelevant to throw away one usually. All right. So this kind of hypothesis that we can actually then reasonably instrument all those functions seems fairly sound. There's a few caveats and like a few non-fatal kind of practicalities actually to work out. One thing worth mentioning at this point is for the tests that I've been doing so far, I've effectively been like rewriting the targets manually to insert the instrumentation. Obviously, you would use like Clang on a source-to-source translator to do that, but once I actually figured out that this was a reasonable path, I haven't gotten around to that. But that's, in my opinion, not a particularly hard thing to do. Right, hypothesis 3 is that we can actually synthesize these predicates and then get reasonable results from that synthesis. As we said already, synthesis itself, we need predicate templates, and then we need a trace of expression values. From that, we can synthesize predicates, and we can evaluate those predicates. And then the output is going to be a list of pairs in the form of predicate boolean, which tells us whether that predicate is either true or false in that particular one. The templates that we ended up going with kind of have a few different forms. The first is we have single variable templates, where you just have a relationship, say, between a variable and 0, or a variable and some other constant. We have multiple variables and a single scope, where you have, say, something plus something is greater than something else, and they're all within the same scope. You have multiple variables and then multiple scopes, so you have something in one scope is bigger than or less than something in another scope. And then you've got all of the above, but you have like expressions as well as variables. When I say expressions, I just mean like any kind of expression that appears in the source code, which we can just like grab, get the result that's calculated, and then store it. As an example, if we have this statement which we saw earlier, we have these recorded state, we would end up in our analysis synthesizing all of these predicates, most of which are complete nonsense, but it doesn't matter because we hope that just under the weight of numbers across hundreds and hundreds of inputs, the ones that are not nonsense and that actually correlate with a crash will end up having some statistical relationship with the crash. Multiple variable predicate synthesis, we need to be a bit more careful. Obviously, we can't just create the product of every variable with every other variable in some sort of expression, because that would be like you quickly get into the billions of possible predicates. So for now, what we do is across for multivariable things, we create inequalities over variables in the same expression and within the same scope, and then inequalities over function arguments across multiple scopes. So the only time we will synthesize predicates across multiple scopes is when those variables are actually used as function arguments. Pretty straightforward. In terms of actually ranking those predicates, we reuse the exact same ranking functions as I saw earlier, or we discussed earlier. The only difference being that we slightly reinterpret the NF and the NP case. If you think about it, previously NF and NP were related to the execution or the non-execution of a line. So lines are either executed or non-executed on a single run, whereas with predicates, they could be evaluated or not evaluated, or they could merely not be observed. So it might be that that predicate simply wasn't observed in that particular line. So there's just a minor reinterpretation, but it's not particularly significant. The actual results of this thing, what it spits out, are something like this. So we have a score here, which is saying like a strength of the relationship between this particular predicate and this particular line and the actual crash. In this particular example, it's for that GD image crop bug we saw a while ago. So what we see is we have a whole bunch of explanatory variables on lines previous to this one. And then we eventually have the actual predicate which describes the root cause of the bug. Were we to then effectively just take those and then put them into the source code, but we'd end up with something that looks like this. And this is kind of what we're aiming for as like an end result from this research. I say artist's impression here, because I haven't actually got around to pulling these into Vim yet. Effectively what I do is I have the predicates open in one.txt and I have the source code open in another window. But I understand that apparently that's not an ideal interface for some people. But I like it. But what you would actually do in a reasonable case is create a Vim plugin to simply pull things in from the .txt so you can see them like this. And what you end up with is a marked up version of your source code where you have basically extra information that you can deduce from the runtime. And you end up here with the description of what the actual bug is, and then for each of these variables, you have descriptions of different predicates that held or didn't hold on them throughout the crashing events. All right. So again, the ability to synthesize and then deduce our ideal result, it seems pretty reasonable to me across all of the test cases that I've worked with. You tend to get in the top, the top ranked results will be a bunch of kind of explanatory or kind of anomaly predicates, and then sooner or later the root cause itself, or something that's kind of close enough to the root cause that allows you to deduce what it is. In terms of performance, the single variable synthesis, if you just use that, is faster than just importing coverage reports because you end up with a much smaller amount of data. And the multivariable synthesis is about equal to the cost of importing coverage reports. The reason I mention this here is I guess your fear would be that this thing takes days to run. It doesn't. It's on the order of seconds rather than days. And in most situations, the top ranked predicates are in fact explanatory for the actual bug. All right, caveats obviously for this. It's a single target. It is just PHP at the moment. I haven't got around, while I'm still integrating Firefox into the corpus, I haven't actually got around to analyzing it yet. And there's still further work. I get the feeling that there's probably going to need to be some change to the predicate templates and the instrumentation. We'll get to deal with memory, lifetime management issues in a precise fashion. And there are also some minor weaknesses, such as I don't filter out. If we have x is less than 0 and x is less or equal to 0, I don't filter them out, despite the fact that it may be the case that x is purely strictly less than 0. So you end up with some extra noise in the results, basically. But that's kind of housekeeping. All right. So as I said, these first three predicates, these first three hypotheses seem to hold based on the crash corpus bugs and the target, which is PHP. The fourth one, I can't conclusively say that we can produce a narrative from this because I'm right now using a text file and the source code, but I don't think there's a huge amount of effort in creating a Vim plugin to just pull that data from the text file. So I'm going to we'll say orange rather than red. I believe in you guys. All right, so we're getting close to the end. I have no idea how far over time I am. I assume it's off time.
You're last, so it's fine.
Great, perfect. So in other words, I'm holding people up from the back. So we execute target software on all crashing and non-crashing inputs. We do that using Clang and fsan test coverage. Again, you want to use this rather than gcov, for the reasons I mentioned. We then perform a statistical analysis of the coverage information to determine the relevant functions. And the GP13 function is the one that seems to work the best. I guess the intuition is that the EF and EP values, which are the number of inputs, or the number of crashing inputs the component is executed on, and the number of crashing inputs the component isn't executed on, are more relevant than the other factors. Then rewrite the target to insert the LTTNG trace points, synthesize the predicates by brute force from templates, and then again perform the same statistical analysis that we use for function level prediction in order to predict the actual predicates that are relevant. So that is pretty much the economics of that. In practice, in terms of timing, these are just the commands you actually run, say, from the repository. It's about 2 to 3 seconds per input to gather the coverage information, 6 to 15 seconds per input to actually then import them into the database and perform the analysis. To actually then predict the functions, so you're talking about a couple of seconds. At the moment, like I said, I'm manually inserting the tracing, but normally source-to-source rewriting for 9 functions is going to be a second. And then your recompilation time. Gathering the actual value trace itself, again, about 2 to 3 seconds per input. And then importing the value traces takes kind of 1 to 15 seconds, depending on what type of, if you're using multivariable synthesis or not. The convenient thing about this particular analysis and algorithm is that there's no dependency between the analysis on one input and another, so it's completely parallelizable. So, and then predicting predicts is quite short. So for example, if you have like 800 inputs and 32 cores, you just split all of your inputs across all of your cores. You don't, there's nothing sequential in the analysis of each individual input. So 800 inputs is about kind of including like crashing and non-crashing inputs, is kind of about the average across the corpus. And you're talking, in order to get the results I was talking about earlier, you're talking like 10 minutes of analysis. So like you make some tea and go back. The reason I mention this is because like a lot of kind of automated program analysis things take like 2 days to run and it doesn't really fit into your workflow. I'm fairly confident with this that it should fit with minimal disruption into some sort of workflow. All right. So, like I said, these were the assumptions we had. They seem to hold. It seems to be like a reasonable approach. The reason I'm kind of saying this is like an experimental thing is because realistically, there's still huge amounts of other work in the academic literature that you could take, and you could like take out parts of what I've done, put in other things. So there's still some experimentation to be done here, but this approach as like a baseline seems to be somewhat functional. There are some practical things that need to be done. Obviously, you've got the actually taking the results, pulling them into Vim or whatever you use to read code, and then the automatic insertion of trace points. There are some conceptual ones. So, for example, what bugs or bug classes does this not work on? There are no race conditions in the corpus at the moment. I have no idea if this is even like remotely a sensible approach to that. What makes the best input set for our purposes? So, for example, with fuzzing, you typically perform minimization. In our context, are we losing information by doing that, or is it giving us a performance benefit? And what happens if we actually go wrong in the first stage? So, for example, if we mispredict the relevant functions, is there some iterative algorithm where we can like work down the list of predicted functions? I don't know. Maybe there is. I assume there is. It's not complicated. All right. So, final thing. In August, I'm doing some program analysis trainings. If you're at Infiltrate, email me. Tell me. There'll be like a discount in it for you. Other than that, if you have any questions about this or you want access to the source code, I guess more importantly, just drop me an email. And I guess that's question time and then the bar.
Cool.
Thank you.
So who predictably in the back would like to ask a question?
Is that like a pun, predictably? No.
Could have been
Never mind.
if I was boss, but I'm not. All right, so
Sweet.
cool. Tonight, those of you who enjoy drinks and dinner, 7 o'clock, it's on the La Cote lawn, I assume is how that's pronounced? No? Who knows? I have no idea. Anyway, it's outside toward the ocean. There'll be a lawn, there's signs that will say Infiltrate on it. It starts at 7. Tomorrow, breakfast is at 8, and then I think we start at 9. Is it 9:30? Are we starting a little later?
I don't know.
You're Sean, you should know. Yes, 9:15. So we start 15 whole minutes later. So that's slightly more sleep for you. Thank you for coming and filling up the room and being a good audience. And I will see you outside.